In today's video, we will continue with our discussion on continuous random variables. This is the fourth and the final video in a four-part series. The goal in this would be to introduce the log normal and the beta distributions. The log normal distribution is exactly what it is. We will say that x has the log normal distribution if the ln, that is the natural logarithm of x, has the normal distribution with parameters mu and sigma squared. That is, to put it into symbols, ln of x has the normal distribution with mean mu and variance sigma squared. If x has the log normal distribution, the PDF of x can be calculated as follows. This calculation follows using differentiation under the integral sign by starting with the CDF for the log normal distribution. Note that mu and sigma squared are parameters for ln of x. They are not parameters for x. That is, the expected value of ln x equals mu and the variance of ln x equals sigma squared. If x has the log normal distribution, the expected value of x is going to be e to the mu plus sigma squared over 2, and the variance of x is going to be e to the 2 mu plus sigma squared times e to the sigma squared minus 1. It's important to distinguish the parameters of x and ln of x. We can use the standard normal table or the standard normal distribution to calculate the CDF for the log normal distribution with parameters mu and sigma. This calculation follows as follows, and notice that the CDF of the log normal distribution is exactly the CDF of the standard normal distribution evaluated at ln of x minus mu divided by sigma. This is for all values of x that are greater than 0. The next distribution for today is going to be the beta distribution, which takes values in a finite interval. It is a good distribution to model proportions, which naturally lie inside the interval 0, 1. We will say that a random variable x has the beta distribution with parameters alpha and beta, which are greater than 0, if the PDF of x has the form fx comma semicolon alpha comma beta equal to gamma alpha plus beta divided by gamma alpha times gamma beta times x to the alpha minus 1 times 1 minus x to the beta minus 1. This is defined for all values of x inside the interval 0, 1. This distribution is called the beta distribution because of the beta function, which is defined for values of alpha comma beta as gamma alpha times gamma beta divided by gamma alpha plus beta, defined for all values alpha beta which are greater than 0. In this setting, the PDF of the beta distribution is defined as 1 over beta alpha comma beta times x to the alpha minus 1 times 1 minus x to the beta minus 1 for all values of x between 0 and 1. If x has the beta distribution with parameters alpha comma beta, the expected value of x is equal to alpha divided by alpha plus beta, and the variance equals alpha times beta divided by alpha plus beta the whole square times alpha plus beta plus 1. Note that both the expected value and the variances are numbers that lie between 0 and 1. Now, depending on the values of alpha and beta, the PDF of the beta function is going to have different shapes, and we specify some of the cases here. When alpha is greater than 1 and beta equals 1, we will have the PDF to be strictly increasing. If alpha equals 1 and beta is greater than 1, we will have a strictly decreasing PDF. If both alpha and beta are less than 1, we will get a U-shaped PDF. On the other hand, if alpha equals beta, we will have a symmetric PDF about the value half. In this case, the mean equals half and the variance equals 1 over 4 times 2 alpha plus 1. When alpha equals beta, the beta distribution ends up being the uniform distribution on the interval 0, 1. We finish up by introducing the Cauchy distribution. We say that x has the Cauchy distribution with parameter theta if the PDF of x is f of x semicolon theta equals 1 over pi times 1 over 1 plus x minus theta the whole squared. X and theta are allowed to be any numbers inside the interval minus infinity, infinity. It's an elementary calculation to show that f satisfies properties of being a probability density function for a continuous random variable. And if x has the Cauchy distribution, it has this very interesting property that the expected value and the variance of x do not exist. This becomes even more interesting because the graph of the Cauchy distribution or the PDF of the Cauchy distribution is bell shaped like the normal distribution. However, it has very heavy tails. So these heavy tails are what cause the expected value and the variance to not exist. The Cauchy distribution is related to what is known as the student's t distribution, which plays a very important role in statistical inference. To summarize this video, we have spoken about the log normal distribution with parameters mu and sigma squared, the beta distribution with parameters alpha and beta, and the Cauchy distribution with parameter theta. This is all for today. Take care of yourselves, and I will see you around.